Hi guys, welcome to Learning Electronics Repair. These are the PCBs for the PCBWay 0 to 30 volt, 0 to 10 amp power supply project we've been working with. The original project works just fine. I wanted to modify it so we could use two ATX power supplies to run this because that's the cheapest way that most people can get a hold of a high powered transformer. The original design worked with a 0 to 15 volt dual winding transformer, so it was a very large toroidal transformer, two windings, each 0 to 15 volts, and to get those in high currents are really expensive. So of course on here I wanted to find a cheaper way. Here's one I put together to test out the design. I'll link to the previous videos and I'll also link to the PCB so you guys can buy some of these and have a play with them. These are from PCBWay.com. A set of 5 PCBs unpopulated will cost you $5 plus postage to wherever you are in the world. If you want to go with the economy postage, you're going to pay about another $5 of postage, so you can get 5 of these including postage for $10. But if you use the link in the video below with the special code, then you will get $5 off that, so you'll actually be able to buy 5 of these for $5, including postage to most places. And that's got to be a real bargain. So I'm hoping some of you guys want to build these and play along with this while we figure out how best to implement it. Although this is a 10 amp 30 volt variable power supply, it needs a power input, and this is where the ATX power supplies come in. I'll just show you on this schematic for you. You'll see how this actually connects up. Here is the schematic. You'll probably notice at first that I only fitted one of these TIP3055 output transistors. While I'm testing this, I'm only going to draw up to about 2 amps, so that's fine. It's just really to save any extra expense if something goes wrong and damage the circuit or damage the output transistor. I will only damage one of them. I have about 10 of them here, it's not a problem. It's just a sensible way to do this when you're building these things, I think anyway. You'll see here we have the power supply transformer, okay, 2 times 15 volt windings at 10 amps, 300 VA, that's effectively a 10 amp transformer. We have a large bridge rectifier, some large capacitors, and they feed the power in. And if you look, you'll see that the two 15 volt windings are in series, and we have the center tap which comes to this relay. So the relay can either provide 15 volts into here or 30 volts into here, and the way it does it's quite clever. So we have this little circuit here, we set this potentiometer to a certain voltage and it uses that to trigger the op amp, so it monitors the output here. Okay, the resistor R1 6.8k and now a 10k adjustment form a voltage divider. And if you look at the other input, which is connected to here, again through a voltage divider, it has a Zener diode. Okay, so that's a fixed voltage. So the idea is, for example, when the voltage here gets to say 10 volts on the output, so you turn it up from 1 up to 10, when it reaches 10 and you want to go higher, this then switches the relay and provides extra voltage into the transistors. And the sole intention of this is to reduce the wattage that these transistors need to dissipate. Effectively, the less voltage difference between the input and output of the transistor, the less heat it generates. So that's why we do this. So we set this adjustment so at a certain point we get more voltage coming in and we can increase the voltage further. When it comes down at a certain point, we switch this back to 15 volts input and we can keep decreasing the voltage and it just gives us less wattage dissipated. That's the simple explanation of that. Okay, so hope you were following along. Previously I decided to use 2 ATX power supplies in series, giving me 12 volts and 12 volts, and it doesn't work. We need more voltage coming in here. It does work, I will say, but we get about 5 volts voltage difference across here. So with the 12 volt supply was actually giving me about a maximum of 7 volts out, and I wanted more. Okay, yes, we can set to switch the relay and get more, but then with the 24 volt supply, we still only have about 19 volts coming out, maybe a bit less. So I spent a long time working this circuit out, seeing if I could effectively increase the voltage here with a lower supply. I found I couldn't do it, and so I published it, and there were lots of comments. And amongst the various comments, a lot were very interesting, so a lot of us learned quite a bit from this project. It's great, we all love to learn, I love to learn, okay? It was really interesting, but one of the things that came out of this that I thought, hey, I'll give this a go, was to modify the ATX power supplies so I connected the 5 volt and the 12 volt in series. That would effectively give us about 17 volts here, plus another 17 volts, total of 34, and that should be plenty to drive this, okay? Although you see the transformer giving you 15 volts, this is AC. The actual peak voltage which you get across these capacitors will be somewhat higher. So for a 15 volt transformer, I will be not surprised at all to get 18, 19 volts here. So putting 17 in is not going to be a problem. We can see that in fact is true because there's another connection to this coil through this diode which rectifies it, okay, into a capacitor which smooths it. So we get a DC voltage here, and this voltage comes from the 15 volt winding and it's not switched by the relay. This voltage, V plus, powers these chips, okay, and also the op amp. So the control circuitry runs on a single supply rail. It doesn't switch. The switching voltage only comes into here to give it the higher voltage in for higher voltage out. And look what we have. Rectifier smoothing capacitor V plus. And then we have an 18 volt Zener diode which stabilizes the voltage for here. So the chances are the voltage coming in is not 15 as I say, it's probably nearer to 18, maybe a bit more anyway. So having said all that, let's try putting our two ATX power supplies with the connections of the 5 volt and 12 in series on each one. We may have to then reduce this Zener diode a bit to maybe a 16 volt or something to get a stable voltage here. We need this for the switching to work correctly. But having said that, the ATX power supplies should be stable with the output anyway. But it's just something we can consider, that we may need to just reduce that a little bit. And hopefully then this will work. So let's have a look to see how we are going to modify an ATX power supply to connect the 5 volts and 12 volts in series. To modify the ATX power supply to connect the 5 volts and 12 volts in series, we need to understand on a fundamental basis how the output of the power supply works. I'll give you a quick diagram, always best done with a diagram, but basically what we have is we have the primary of the switch mode power supply transformer, okay, and one end of the primary is actually connected effectively. I've drawn the circuit before so I won't do the whole thing again, but it connects to two switching MOSFETs like so. There's a capacitor here before somebody says, and yes, there's another little inductor here as well before somebody says, but that's basically the circuit. This is your plus 320 volts, this is your 0 volts. More if you have PFC, we won't go into the details too much this time. Your two MOSFETs, and they are switched by the controller. And this switches these on alternately. So what it does is it connects this end of the coil to 320 volts, then to 0, then to 320, then to 0, and so on. And it does it very rapidly. Hundreds of kilohertz, yeah, hundreds of kilohertz. And by doing so, it effectively generates an alternating current in the coil. This capacitor and inductor basically mean that the alternating current is actually effectively a sine wave. Although this is being driven by a square wave, on off, yeah, as you switch these. These components form a resonance circuit which effectively gives a sine wave. Now, we need to get our power supply voltages out of here. So what we have is, we have 3 windings. Okay, one for 3.3 volts, center tap going to ground. We have here diode, Schottky diode, fast switching diodes, 2 of them, connected like so. Then we will have, it will vary a bit, but basically we'll have an electrolytic capacitor connecting to ground. We'll have an inductor. We'll have another electrolytic capacitor connecting to ground. And this will go to out. Okay? And we have this circuit 3 times over. So we'll have a 3.3 volt. And the same for a 5 volt and a 12 volt. So I'll just draw them very quickly for you. Here you go. Okay. Yes, I messed up the capacitor on this one, but you can all see which way it is. All right. So 3.3, 5 and 12. But I'm actually, because all these circuits are identical, you can see they're identical. To make this diagram work easier, I'm going to say this is the 12 volt supply and this is the 5 volt supply. You'll see why in a minute. Okay. Now, the power supply has to monitor the output voltage from the ATX, and the one it monitors is this one, the 3.3. So usually, internally on the power supply, there will be a resistor here to ground. And that's to put some load on this capacitor so that when the power supply isn't putting much power in, this resistor can start to discharge this capacitor. If we didn't do that, when effectively the control circuit detected there was enough voltage, 3.3, it would send a signal back to the power supply controller to reduce the drive, but the voltage in this capacitor wouldn't discharge because there's nothing to discharge it. Okay, especially when it's not attached to a motherboard or anything. So what will happen is this capacitor can't discharge. So the power supply says, oh, I need to reduce the drive, so it reduces it some more. But this capacitor can't discharge. So it reduces the drive down as far as it can, and this capacitor still won't discharge, and that's what happens, it can't go any lower. So your 12 volt and your 5 volt both go down in voltage, they become unstable. Okay, to make the regulation work, you must always have some load here. So that's why they put a resistor here. And it might be 20 ohms or something like that to draw 100 milliamps or so. It doesn't need to be drawing a lot of power. It's usually a 1 or 2 watt resistor. And as long as this can draw some power, what happens is then when we have 3.3 volts and the feedback circuit says reduce the drive, it reduces the drive. This resistor is still drawing as much power, so it starts to discharge this capacitor, the voltage starts to fall, and the feedback circuit says, the voltage is going down, give it more drive, bring it back up again. You see that needs to be there, otherwise it can't stabilize the output, okay? So that's what we have. Now, in the previous video, we talked about how to connect 2 ATX power supplies in series. We effectively have to disconnect the safety ground from the output ground. We still have a safety ground. I won't go into all the details again now, but I did explain it. I'll link it from here. And you'll see that if we don't have a disconnection between safety ground and ground, we will effectively short out one of the power supplies when we put them in series. So we've already done that, yeah? And if you don't understand why, guys, just look in the description to this video and I will put a link to that video, and I'll put a little note on it saying why we need to disconnect the ground when we put ATX in series, and you'll understand it, okay? But for all of those of you who already watched the videos, you don't want to see it again. I'm stuck between a rock and a hard place, yeah? So that's my get out. So anyway, back to this. These diodes here and here and here, if you've ever looked at an ATX power supply, you'll know that we have 3 pin devices which are double diodes, okay? And inside here, effectively, you'll see we have a symbol. like this. Okay, so 2 diodes. This is the cathode, this is the common cathode. Okay, and those are the anodes. So that's what it literally is. It's 2 diodes inside one package, connected like that. Okay, the 2 ends of the diodes, if you like, the 2 outer pins, connect to either end of the winding, and we have one on the 5V, we have another on the 12, and another on the 3.3. So all this circuit here doesn't have a connection to ground apart from the capacitors, okay, and the center tap of the winding. Now what we need to do is to put our 12 volts in series with the 5 volts, and the way we do that is this. If we disconnect, if we take a different colored pen, now if we disconnect this center pin on this transformer from ground and we connect it to our 5V out, we'll now have 5 volts on here. Okay, like so. If we now connect these capacitors to here also, this will also be 5V. So the voltage across these capacitors will not change, okay? What will happen is now, if we use our multimeter and we connect from here, I've got our multimeter, and we connect to here, always draw an analog one, don't ask me why, and we connect the other end of our multimeter to here, we'll see 5V, okay? If instead we connect our multimeter to here from ground, we will see 17V. 5 plus 12 is 17V. But if we connect our multimeter between here and here, we still see 12V. Hence why I say the voltage across these capacitors will not change. We will not blow up the 16V capacitors on the 12V rail. So that's what we need to do. We need to disconnect the center tap from here and the 2 grounds from these capacitors and connect them not to ground but to the 5V rail. Okay guys, hope that made sense. Do you want to see if it blows up or what? I'm pretty sure you do, yeah? Let's try it. Here are the 2 ATX power supplies we connected in series. So first of all, let's disconnect them from each other. Okay, we will connect them in series again afterwards, but just for now this will make it easy to work on them. Okay, so here's one of our power supplies. So we'll modify them both. They're not the same design, they are different as you see, but we know what the principle is. The principle will be the same. Just before we make this modification, let's see how much power, the ampage, we can get out of our modified 17V supply. Well, basically, so the current flows through the coil, through the diodes, through the inductor, into this coil, through the diodes, through the inductor to the output. So you can see the current path is continuous. Therefore, the maximum current we can get out of here will be whichever of the 2 supplies is the lowest. So whichever can supply, for example, if this can supply 5 amps and this can supply 10 amps, the maximum we can get is 5. We can't go higher than the current rating of the lower of the 2 supplies. Let's see what they are. Well, here's one of them. So you'll see on this one, the 5V is up to 30 amps and the 12 is 19. So the highest we can get is 19 amps in total off our 17V rail, which is more than enough. And the other one, somewhere during our previous videos and experimentation, I've lost the lid, so I don't know, but I can refer back to the earlier video, but I seem to recall it was 14 amps on the 12V, so the total we can have with both in series is 14 amps, and the 5V was more than the 14. Okay, so I think 14 amps is going to be the limit with both these modified supplies in series. And that, guys, I think is more than enough. To make this easy, I'm going to disconnect all these wires. All I need when I'm finished is some black wires for ground and some yellow wires for 12 volts. The 3.3 we don't need to be connected to. I need to connect the green wire to ground, but I can do that over here, and that's all I need. So let's take all these cables off, and then we'll be able to see much easier what we're doing here. I've desoldered all the wires now. This one, this black one, actually connects from the ground, from the standby supply, and connects to the ground of the main supply. So this is effectively just connecting the ground of the two supplies together. We need that because this transformer is driving the 3.3, the 12 and the 5 volts, and this is the 5 volt standby, and these separate supplies. That's why we have this wire. It could have been a PCB track, but obviously here they just put a piece of wire. This is the 5 volt standby. I don't think of any reason that we actually really need that, but it's there in case we do, otherwise I can just desolder it. And this is the green wire, so I need to solder this to ground also, and that means the power supply will automatically start when I put the mains power on. We can see now we have the double diodes down here. I'll try and show you a little bit more clearly. Okay. Remove the cobwebs. So this one, you can clearly see the two diodes as I drew it on the quick circuit diagram. The next one says AC, AC and plus, but that's basically the same thing. And this one again, AC, AC and plus. If we just get a little bit of light down there, yeah, you can see it clearly now. So those are the output diodes for the 3 voltage supplies. It looks like this power supply isn't quite the same as the example one that I drew. So we have a large inductor here. This is probably 2 inductors actually. There's 2 coils, so I think probably one of the coils is on this output, which is the 5 volt, I'm thinking, because it's closest to there, and the other one is probably on the 12 volt, which is the next one. Okay, but I may be wrong. And then we have another inductor here, and maybe this is on the 3.3. One of these is quite possibly, or both of them even, the load resistors on the 3.3 that helps to keep the stabilization working as I was describing. So we'll mark on the other side of the board with some colored pen so we know which one is which, and then we can trace to see where they go to. This then is ground, so I'll put a black mark here. Okay, that's ground. The next one is 5 volts, so we'll put red on that. Okay. The next one is 12 volts, but I don't have a yellow marker pen, so I'll put a little bit of green on it, I guess. But you probably can't see it very well. Okay. And then the last one is the 3.3, which is the orange, so we'll put orange on that. So we can see which one is which. Now let's see where they go to. Okay. Black is ground, and we can see that here. This is where I actually put this little bit of wire in when I disconnected the safety ground from the output ground, so we could put the 2 ATX in series. This is ground coming up here. Okay, this is the 5 volts, and that will go to one of the diodes. Now you see the diodes, there's one here, the larger one, there's one of the smaller ones there, and the smaller one there. And the middle pin is the output from the diodes. So let's have a look to see where these go. 5 volts, I'm guessing it's probably here. Yes, that definitely goes to there, and it doesn't go to here or here. Okay, so we know this one here is the 5 volt. Okay, the 3.3 volt, which is the orange one, does that go to this one? Yeah, that goes to this one. Okay, and again, it doesn't go to the other ones, of course, because they're not shorted to each other. So that is the 3.3 here. And then the other one will be the 12. We know this is the 12 volt, and that can only really go to the other one, which is here. Okay, so that is your 12 volt. I don't think I can mark it easily. This green pen doesn't seem to do very much. Well, it does, you just can't see it very well. Okay, so that's the 3 outputs. Now what we want to do is disconnect the ground on the 12 volt supply and connect it to the 5 volt, basically, to put the 2 in series. So where's ground? Well, this is the transformer. We can see the pins here, okay? And I can see straight away that she's not wired up in the way that I drew that diagram as an example. What we have is 5 volts is here, and that goes to these 2 pins. This is the outer pins of the diodes, which will read like a short because they are both going to the winding. So these 2 pins and these 2 pins form one winding, okay? We have only 2 more of these here, which is another winding. And this winding must supply one of the other diodes. Which one? Well, it supplies this one. You can see the track comes to here and it comes to here. Okay, so that's where it goes to. And we know this is the 12 volts. So that is the 12 volts. So the 12 volts comes from either end of this winding, and the 5 volts comes from either end of this winding. So where does the 3.3 come from? Well, if you look, it comes from the same winding as the 5. So we have a track going over here, and this is the diode for the 3.3. There. One end of that diode connects directly to the same winding as the 5, and the other one comes through something here. You see there? It comes through a component here, back to the 5 volt winding. So both 3.3 and 5 are coming from the same place on the transformer. But what's this on the 3.3? Let's have a look. Ah, that's another inductor here. I'll draw that on our piece of paper. I'll just update the little diagram to show how that is actually wired, and hopefully try to explain to you how we get both 3.3 and 5 volts from the same transformer winding, because the winding on the transformer obviously going to both is the same voltage going to both. Okay, but the main question is now is where is the ground, because we need to connect the ground, and each of these 2 windings will have a center tap. Well, we can see here this is ground and this goes to this pin. And if we look, because an inductor is like a short, we can see a short effectively from here to each of the windings, but it's not a short. It's just that the transformer windings have very low resistance. If we used a MilliOhm meter or an ESR meter, we would see that. But anyway, this must be the ground. And if we have a look to see where that comes from, it comes from here. Okay, so what we must have inside here is the center taps from both of the windings. There may even be 3 windings, 2 in parallel for the 3.3 and 5. So we'll have 2 or 3 enameled wires coming down to this point. This is ground. If we unsolder this and separate the wires out, we should be able to figure out which is the ground from our 12 volt. So let's do that. I'll try braid first, see if that helps to desolder this. Otherwise I'll use the vacuum tool, or I'll just grab hold of this thick wire and just pull it out of the board when I've got the solder melted. Okay, but it is moving, so I think this is going to work. Come to the other side of it. So we're getting plenty of heat in there. Yeah, that's free now. Okay, so we can pull that wire out of the board, and then let's see what we have. And as I say, it should be 2 or 3 wires twisted together. Well, it is out. Try and bend it upwards. Okay, very stiff. There. And it looks like it is several wires twisted together. So while that's cooling down, let's just make a alteration on our little diagram, and I'll show you how that other inductor is wired for the 3.3 volts. It looks like what we have then is the primary of the switch mode transformer, and then we actually have 2 secondaries. One of the secondaries on its own is the 12 volt supply. So this has the two diodes, inductor, diode, capacitor to ground, and probably another one, although we haven't looked exactly yet, but most likely we have that, and the center tap going to ground, which is the one we're going to disconnect. Then we have another winding on here, and this one goes to the 5 volt supply. Five volts. Like so. And then we have connected from here the 3.3. I'll do it with a different coloured pen again. I can't quite lay my hands on my pink pen, so we'll use the blue one. So from here and from here, you have connections. Okay. One of them, I'm not sure which one, but one of them goes through a inductor and then goes to a diode coming out like so. This is your 3.3 volts. Ground. Okay. And the other one goes directly to the other diode, to there. So that's what we actually have. And again on here is the center tap to ground. What this inductor is doing is effectively acting like a resistor. So an inductor coil at high frequency has inductance or reactance, it's resistance basically. So at the frequency this power supply operates, this inductor will drop voltage like a resistor would drop voltage across it. And that's how they're getting rid of the extra 1.7 volts. Yeah. They're using an inductor instead of a resistor because it doesn't get as hot effectively. It's a nice thick piece of wire, so it's not going to dissipate as much heat as a resistor would. That's why it's done that. If you put a resistor here somewhere, then what you would effectively have is 1.7 volts across that resistor, and the same current would be flowing through it as through the load, so it would be generating quite a lot of heat. Heat being watts and watts being voltage times current. So that's what they're doing, and that's how they're getting the two voltages from one. It's not relevant to what we want to do, it's just interesting. Yeah. Comments below, guys. So we still want to disconnect this ground and connect it to here. I mentioned before that we could do that and leave the existing capacitors in here, because one end of the capacitors would be connected to 5 volt, one would be to 12 volt, so the voltage across them wouldn't increase, they wouldn't blow if, for example, there were 16 volt capacitors. But there's another way we can do that. We could replace the existing capacitors with 25 volt capacitors and leave them connected from this, which is now going to be 17 volts, to ground. It may be actually easier to do that because you haven't got to effectively take them out the board and extend one of the legs of each to where we want to go. So I'll probably do it this way. But if you were trying to do this on a budget and you don't have other suitable capacitors at 25 volts of the same capacitance as the original ones, you could do it the other way. Yeah, you could actually do what I said and use those capacitors. But I'm probably going to do it this way, assuming I have some suitable capacitors, which I probably do have. Okay, so let's have a look at that wire we unsoldered now, and let's see if we can find out which of the wires is this one. Well, it looks like these wires are twisted and soldered pretty much all the way down. At the other end, I can see enamel wire there, so it's like I can get to where I want to go, but it's going to be further back in here. It looks like I'll have to strip all this heat shrink type sleeving off to get to what I want. Okay, I'm so far back down here now you can see the enameled wire, so we can separate them. It's not going to be easy to do this, and to make life more difficult we have this big heatsink in the way and the one the other side as well. But I think if we unsolder this one, this is the heatsink with the diodes on, then it'll be much easier to get here to work. I mean, sure, you could fiddle around down the side here, but they're quite sharp against your fingers. I think overall, it's probably better to take the time to unsolder this and get at it easier. But I guess that depends on how much you like to fiddle around and then how much you like to think, well, I need to unsolder this anyway. I should have done it in the first place. Yeah. I might actually be able to just remove the 3 screws actually, and then leave the components in place. Let's see which is the easiest way to do it. But whichever is the easiest, that's what I will do. Well, I did it by a kind of hybrid method. So I undid the 2 bolts here because I could easily get to them, and then I just unsoldered these 3 legs and the 2 metal pins that hold this down, and we have it. Notice that there are these washers underneath these 2 double diodes because they have metal tabs, and they also have little plastic insulators on here as well to make sure that the tab does not connect to the metalwork or is bolted to it through anything conductive, so we have to be sure to put those back on. I'll put those safe. Best way, by the way, just a hint, just screw it in a little bit so you can't lose these things. Because, believe me, if you can lose these things, you will lose these things. Yeah. Years of experience have taught me that one. So if we just do so, and the same with the other one, then they can't go anywhere. Unless, of course, you lose the whole thing. That's another possibility. Yeah. If you can lose the whole thing, you will. Okay, but at least you're looking for one thing then. Right, so we'll put those on one side. Hopefully where we can't lose them. Now we can get to this. So I need to unravel these wires. I mean, I could just cut them off here where they're not soldered and untwist them, but I think I'll try and get it hot and maybe get a pair of pliers and try to get it started. If I can start it unraveling, then I can just heat it up and effectively unravel it, I think. Well, that's the theory anyway. I've never tried this before, by the way, guys. This is the first for me. It was a suggestion from a subscriber that I can do this. Yeah, so you can't blame it totally on me when it all goes horribly wrong, but let's try. Well, by trying a technique that is as much luck as judgment, I'm managing to separate them. I'll show you how I'm doing it. So I added a bit of fresh solder and flux, okay, onto the end of it. Got some flux in. And then I'm using a pair of these sort of cutters, yeah. So I'm effectively just warming the whole thing up and then grabbing the end of it and untwisting, okay, like so. And you can see it's coming apart. So I just need to unravel these a bit further, and then hopefully we'll get somewhere with this. Well, I got it. I think I'm far enough down here now to be onto the insulated part. It looks like there's possibly 3 pairs here. So that kind of makes some sense if we have effectively 2 windings in parallel here. Each one will have a center tap. That's 2 of them, and then another one for here. So there may well be 3 pairs of wires here. If that's the case, then 1 pair will be the center tap for this winding, and the other 2 will be the center taps for these. So let's have a look, see if we can figure that out. If I'm wrong, of course, these will also be all connected to each other. Those two seem to connect together. I'm expecting two of them to, another one not. No, it looks like they all connect together. So it's looking like I still need to effectively unravel these pairs as well before we can isolate the ones we want. Yeah, this still connects to here. This still connects to here, so we still have a common ground. Okay, we now have 6 separate wires. I'm still expecting that 4 of them will effectively connect to each other because the ends of 2 of the windings are connected to each other, I think. Let's see. Let's see. Well, that connects to there. Connects to there. But doesn't connect to that one, okay? Doesn't connect to this one. But should connect to here. No, in fact it doesn't, okay. So what do we have? We have 1, 2, 3. All connecting together. But not connecting to the other 3, okay? Are these 3 connected to each other? Yes. Yes. So we have these 3 connected together and these 3 connected together. Hopefully then, otherwise this is not going to work, that one set of 3 will go to the center tap of the 12 volt winding. Okay, let's see. So this is the winding that gives a 3.3 and 5. Does that go to one set of these? Doesn't go to here. Okay, I'll just get onto it. You can see where I am. I'm on there. Doesn't connect to these, but it must connect to these. Okay, so those 3 are the center tap for this winding. Then the other 3 must be the center tap for this winding. Yes, they are. So those 3 are the center tap for the 12 volt winding, and these 3 are the center tap for the other winding, which is both the 5 and the 3.3. So these 3 we need to stick back into there, and the other 3 we need to connect to the 5 volts. Okay, guys, as you can see, I have desoldered the transformer, and that's because I couldn't work out how these connect to the various windings if these are center taps. So what I've done is I've taken my MilliOhm meter and started to measure the resistance between various points. So for example, pins 3 and 4, if we want to go 1, 2, 3, 4 that way, call them 3 and 4, are actually basically connected to each other. And for example, if we read from this ground point, I've called these ground 1, 2, 3, 4, 5 and 6. So ground 1 to pin 6, we read about 10.3, 10.1 ohms. And to pin 1, we read about 21 ohms. Okay, and between the 2 is about 12. So this isn't a center tap. This is one end of the winding, which is ground. That effectively is the center tap, if you like, about 10 ohms. And that is the other end, if you like, about 21. So it's a slightly longer winding than this winding, for example. And we find the same looking through all the various connections on here. So the point is, this is not wired up anything like I drew that diagram of how I thought the ATX power supply would work. But I will show you how it is wired up. It's actually wired up like this. So these are the ground wires, as I call them, ground 1, 2, 3, 4, 5 and 6. I haven't labelled it, but it's there, okay. And what you can see here is effectively you have 3 separate windings all connected to this diode, which is 5 volts. But one of the windings, the one between pin 6 and pin 1, has a tap on it. So we could measure, as we just did, from ground 1 to here about 10.4 milliohms, from here to here 21.9. And this end of this winding is the 12 volt to here. Okay, so this winding is generating 5 volts and 12 volts, and the other two are 5 volts and 5 volts. This is where the highest current is. And then we have the same thing again, which I've drawn here slightly different, but it's the same thing. So we have 1, 2, 3 windings all generating into the 5 volts again to match those 3. And one of them again has a center tap on, or not quite center, it's a little bit off center, because this is 5 volts and this is 7, giving 12. Okay, so again this one has the tap on and goes to here. That's your 2 12 volts. Your 3.3 is like I thought, so one diode comes from here and the other one comes from here via this inductor coil to there. So you can clearly see these 1, 2, 3 windings are generating 5 volts and feeding half of the 3.3. And these again, 1, 2, 3 are generating the 5 volts or half of it and half of the 3.3. And then the 12 volts comes from these 2 extended windings with the tap here. So the point is I'm trying to make from all this is that the subscriber who said just connect the 5 volts and 12 volts in series to make 17 on the ATX power supply, I don't see how he does it. I mean, maybe they're not all the same, but I'm sure you can see from my ATX power supply the way the transformer is wound, it's impossible to disconnect the ground from the 12 volt winding and connect it to the 5 volts out. You can't. Unless, I guess, you unwound the transformer and somehow disconnected that bit and connected it to there, but this isn't AC, so it still wouldn't work. So guys, I don't believe it's possible. Yeah. And I also think we've all learned something. Again, I've certainly learned something, because I didn't realise that things were wired up like this. And as I said, maybe it isn't all of them, but it's certainly mine, and I chose one at random, so most likely that means I was just damn unlucky. Yeah. But we could say the other side of the coin, if I picked one at random and it was wired like this, probably at least half of them are. Yeah. We can discuss the odds against that and Sod's law, as they call it, in the comments below. Yeah. But that's what we have. So we're not going to be able to use the 2 ATX as I wanted to run the power supply board. I did think for a moment we may still be able to do this, because this thick red line here, or pink line, is actually showing that these 2 points are connected together on the PCB track. So if we disconnected that there, effectively what we would have is we would have 2 secondaries now giving 5 volts into here. And this one wouldn't be connected here, so this would give us 12 volts into here. But we'd also want to do the same thing on this particular winding. And in this case, this is actually connected together on the transformer. I've even spread all the wires out just to make sure I haven't got something connecting here, and we can clearly see it. Pin 3 to pin 4, okay? Are connected together. So those windings effectively are joined in the transformer. But there's another part of the story, because several videos ago on this long PCBWay saga, I had a different idea, so I'm going to try this 2 different ways. So let's look at the other idea. And here is plan B. So this is off an old mixer amplifier, a scrap one. The actual mixer part of it, most of it was missing, but this mostly seems to be here. So we have in here a large transformer, a nice big relay actually, some big capacitors, 10,000 microfarad, 63 volts, big bridge rectifier, and we have another little regulator board here. So this transformer actually has 2 windings on it. It's marked down the side there, but it's a little bit difficult to show you in there, but I have had a look. So what we have here is one output is 18V-18, so that's this one, okay, which is similar to what was used on that project originally. This is 2 amps. And this winding is 40-040 at 4.3 amps. So I think we can possibly use this. We would have to look at the rating of the output transistors on here. We can certainly drive the 18 volts from here, 18 and 36 if we want, but that will only give us 2 amps. I'm thinking we can probably do something with these and give us another 4.3 amps. So that actually would make quite a decent power supply. Maybe using more than one of these, so the idea being that would then give us a nice symmetrical supply up to say 35 volts plus and minus. That's quite a nice thing to have. We can also use this as a secondary supply. A fixed plus and minus 15 might be quite nice to have. Or again, maybe we can do something like plus minus 12, maybe make some sort of dual supply out of this. We have plenty of PCBs, okay? We have plenty of PCBs. And we have quite a lot of space inside here to fit our parts. We have a nice big heat sink. We have a big fan behind it. So I think we have here quite a lot of things we can use. We may even be able to use these output transistors that are on these amplifier modules. They may be higher rated than the ones we have, and they will certainly withstand the voltage because that's what the amplifier was doing. So let's continue our PCBWay project. Okay, if you guys are interested, find something scrap like I have with this, order some of these from PCBWay, 5 of them for $10 with the postage, and if you set up a new account giving the link that I have in the description, that'll be 5 for $5, and we can all play along, I think. So I hope you enjoyed that video. I believe this is being something of an epic, but I think we've all learned quite a lot along the way, so I actually think it's been really rather worthwhile. You guys, I guess, will have your own opinions, and we can hear them in the comments below. I look forward to hearing from you all, and I also look forward to seeing you all soon on another Learning Electronics Repair video. Ciao for now, guys.